is right, here is the outline of my talk. First, I will formulate the strong CP problem and very briefly recall the existing solutions we have. And then I will focus on theories which realize spontaneous CP violation with the aim to formulate general conditions to solve the strong CP problem. So after that, I will show how these conditions can be realized in a quantum field theory, in particular supersymmetric QFT, with a local flavour symmetry. And the second part of my talk will be devoted to the so-called modular invariance. I will try to explain what it is and how it helps to solve the strong CP problem. So I will present you with concrete modular invariant models we proposed, and finally discuss the corrections to the desired result. Okay, so let's go step by step. A strong CP problem consists in the fact that the QCD Lagrangian has two parameters or two terms which violate CP. In particular, CP can be violated in the Quark mass matrix, and also by this GG dual term, so this coefficient in front of this operator, theta QCD, also violates CP. And actually, physical quantity is given by the sum of this theta QCD and the phase of the determinant of the Quark mass matrix. So this is CP violating physical parameter, which in particular enters the neutron electric dipole moment. And the neutron electric dipole moment is very much constrained. Actually, from the experiment, we know that it is smaller than roughly 10 to the minus 26 E per centimeter. This translates to a bound on this theta bar parameter that it should be less than 10 to the minus 10. And the question arises, why so small? But actually, it's only one side of this strong CP problem. Another side that we know that in the weak interactions, in particular in the CKM mixing matrix, we have an order 1 CKM phase which violates CP. So how comes this parameter is of order 1 and apparently there is no CP violation in the strong interaction? So the most known solution to this puzzle is the hypothesis of the existence of the axion. So axion is a hypothetical scalar field, and the idea is to promote this theta bar to a dynamical scalar field which couples in particular to this GG dual. So now the QCD generates a potential for these axions, and this potential is such that the minimum is at 0. So somehow axion washes out CP violation in QCD. So this solution requires the introduction of a new global U1 symmetry, so-called U1 PK queen due to PK and queen. And this symmetry is spontaneously broken, such that axion is a Goldstone boson. To be more precise, the symmetry is anomalous under QCD, and this means that axion is not massless, but it is pseudo-Goldstone boson, so it has a small mass. So this is, of course, nice because it provides a clear experimental target. However, so far, the axion has not been found. And moreover, on the theoretical side, there are also some problems, in particular the quality problem, which is very briefly the fact that even if we manage to have this solution, in particular, there are corrections from higher dimensional operators, which scale as the FA over Planck mass. And then if FA is not very below than Planck mass, then one has to worry about these corrections because the bound on theta bar is very stringent. So in a concrete UV model, this U1 should be better an accidental symmetry of a very good quality. Okay, the second type of solutions is based on the assumption that either parity or CP is a good symmetry of the UV theory. And indeed, if we look at this GG dual term, we can see that it is P odd, but C even, and thus also CP odd. So if for any reason P or CP is a good symmetry of the UV, then it kills these terms, and then the challenge is to break this P or CP spontaneously in such a way to keep theta bar 0, but produce order 1 phase in the CKM matrix. So note that in the standard model, actually both parity and CP are broken explicitly, so this calls for BSM extensions. And very briefly on P. So P invariant theory requires either the extension of the field content of our theory or a new gauge symmetry. In particular, probably the most natural example is the left-right symmetry. So if there are no additional mirror fermions, let's think about left-right symmetry, then the Yukawa matrices, they actually Hermitian. And if the Higgs waves also real, then quark mass matrix is also Hermitian. So if they are Hermitian, the determinant is real and it can have 0 phase. Another option is to add mirror fermions. Then in these models, which are discussed in these references here, what is happening is the conciliation between the contribution from the ordinary fermions and mirror fermions. And this conciliation ensures the fact that the phase of the determinant is 0 at 3 length. So CP actually does not require so drastic modification of our theory, because we know that in the standard model, CP is broken by Yukawas. So the idea here is to promote Yukawa couplings to dynamical variables and then break CP spontaneously. And actually, I will focus on my talk on this option. Till now, perhaps the most known example in this class of models is the models due to Nelson and Barr from 40 years ago. So these models, they assume existence of new heavy vector-like quarks, this Q prime, and a set of scalars with CP violating waves. And then one engineers the full quark mass matrix for light and heavy quarks in this way. So the gauge symmetry, standard model gauge symmetry, is broken only in this, let's say, purely standard model sector, light sector, and then the CP is broken in the mix in between heavy and light quarks. So, and here there is 0, which would be good to enforce by symmetry, but in principle, at this point is just an ansatz. So CP is a symmetry. This means that all couplings are real, and the determinant of this mass matrix is clearly real and can be made positive, such that the argdet is 0. Finally, light quark mass matrix depends in a non-trivial way on this CP violating waves of this scalar Z, and this can generate delta CKM. So this is the idea. However, in this particular realization, we still need some additional matter. There is also some tuning between the scales of these waves and, let's say, Planck scale, and moreover, loop correction. So this nice review by Dine and Draper summarizes the challenges to Nelson-Barr models. So now let me try to formulate generic conditions under which strong CP problem gets resolved in theories with spontaneous CP violation. So I start with a very toy model with only 2 generations of fermions. And from now on, instead of writing right-handed quarks, I will write UC and DC, because later I will require supersymmetry. But basically here they are just right-handed quarks. So now I assume that my mass matrix, which is 2 by 2, has this form. So basically each entry up to a real constant is proportional to some power of Z. Then a full quark mass matrix, which is given by the direct sum of down and up, it has this determinant, no? And I want this determinant to be a positive constant to annihilate its phase. So now I ask myself, what should I do in order to have the determinant proportional to some power of Z? Then you look at this equation and see that in particular, if 1, 1 plus 2, 2 equals 1, 2 plus 2, 1, then indeed the Z factorizes, and the same in the up sector, and the determinant becomes some real constant times this complex number Z to the power of D, and D given by this sum here. So now, if this D is 0, then the determinant is a Z-independent real constant, something what I need. Okay, let me look in more detail. So in particular, interesting class of solution to these equations is to assume that the power of each entry in the mass matrix is given by a sum of, let's call them charges, of right-handed, left-handed quarks and Higgses. Then, okay, these charges, they actually not uniquely determined. They're determined by some up to some additive constants. And as we will see, they can be interpreted as charges in models with U1 flavor symmetry, or as modular weights in models with modular symmetry. So in roughly 20 minutes, I will try to explain what this modular symmetry is and how it works. Till now, let's consider the U1. So let's assume the matter fields, they transform with these phase rotations, and just by our convention, I will write here minus k, and for scalars, for the charge, I will write plus k then. Then this is the standard term in my Yukawa Lagrangian, and then indeed you can see that in order to compensate the charges of the matter fields, this KDIJ should be nothing but the sum of them. And then this full degree of the determinant is given by this equation here. And basically this is the idea, no? To get that the mass matrix is such that the determinant does not depend on Z. Okay, so here a bit more on this toy model. So I assume I assign the charges such that in the first generation of right-handed quarks, they are positive. Second generation, they are negative and equal. And for left-handed quarks, the situation is opposite. Then we obtain the simple mass matrices. So here we have a positive power of Z. Here we have a negative power of Z. In particular, so these two one elements in the limit when Z goes to 0, they become singular. And what does it mean? It means that if we consider this setup as an effective field theory, then in the full theory, we have some would-be heavy states. When we integrate them out, they accidentally becomes massless. So in this limit, the EFT breaks down. So saying differently, if let's say I don't want to have such states, no, and don't want to have breakdown of my EFT, then I just should impose that there are no negative powers of Z. And this leads me to assume that D21 and U21 should be 0. Then my mass matrices have this very simple form. So 0 here, real constants on the diagonal, and some dependence on Z in this off-diagonal term. By the way, if you have any questions, just feel free to interrupt me. Okay, so now, of course, we know that 2 generations, they are not enough to produce physical CP violation. So then we need to go a realistic case with 3 generations of quarks. However, if I have 3 generations of quarks and only 1 complex scalar Z, it can be shown that this is still not enough to produce physical CP violation, because basically the phase of this Z can be rephased away. So what we need, 3 generations of quarks and at least 2 complex scalars, Z1 and Z2, with a relative phase, which will then lead to, let's say, physical delta CKM. So a simple example, where I assume no singularities in my mass matrices and 2 scalars, 1 singly charged and 1 double charged. Then I assign the charges -1, 0, 1 to both right-handed and left-handed quarks and assume that Higgs is not charged. Then immediately I end up with this mass matrix in which this left triangular block is 0. On the anti-diagonal, I have real constants, and complexity sits in the elements 2, 3, 3, 2, and 3, 3. Crucial thing here that in element 3, 3, actually I have two independent combinations, z plus square and z plus plus. And if the phases are not aligned, then I will produce physical CP violation. So then one can sit down and derive general conditions to have such mass matrices, and they go as follows. So first, I assume the U-covers to be polynomials in these scalars z, and the powers of these polynomials only positive to avoid singularities. Second, each element in the U-cover matrix should be a weighted homogeneous polynomial of degree k, I, j, q. And then, if this is the case, the determinant of these U-covers is also a weighted homogeneous polynomial of degree, which is simply given by the sum of this case on the diagonal. Finally, the total degree, which is given by the sum of up and down, should cancel. So here, just a concrete realization. So I assume, as before, that each element in the U-cover simply carries this power, which is given by the sum of right-handed, left-handed, and Higgses charges. Then it's simple to see that the degree of the determinant is nothing but this sum over the right-handed, left-handed quarks and the generations, plus the Higgs if Higgs is charged. So then the final condition is that D, this degree of the determinant of the full quark mass matrix, is simply this sum and it should vanish. Okay, so now if I assume only 3 generations of quarks, so no heavy quarks, only standard model, and this texture for U-covers, then actually there are only 3 inequivalent textures up to, let's say, permutations of rows and columns. So the first one is trivial because then I don't have dependence on that. So is no complexity, not interesting, and 2 interesting patterns. In one pattern, we have, let's say, 5 constant elements, 2 zeros, and 2 elements where we have non-trivial dependence on z. And then this pattern, which I already showed you on some simple examples, with 3 zeros, 3 real constants, and 3 complex elements. So now the question, can I realize these patterns in a self-consistent quantum field theoretical model? And the answer is yes. So the first thing that I assumed that my U-covers depend only on z and not on complex conjugate variables. So this is somehow calls for supersymmetry, because indeed in supersymmetry, the superpotential is a holomorphic function of my fields. So this is a simple n equals 1 global supersymmetry action, which is defined in terms of 3 functions. Köhler potential, which encodes kinetic terms and gauge interactions. Superpotential, which will be of interest to us because it encodes U-cover interactions, and gauge kinetic function, which contains in principle gauge coupling and a bare theta QCD term. So here phi denotes collectively the matter field I have in my MSSM, and Z now they're promoted to, let's say, dimensionless gauge invariant chiral superfields, which will break actually my flavor and CP symmetries. So now, in addition to supersymmetry, to realize the general conditions I talked about, I need to require the invariance of my theory under these, let's say, flavor transformations, which act on chiral superfield. So lambda is transformation, k is associated charge or weight. So now we have in principle many possibilities. These transformations, they can be either global or local. If they local, they form a gauge group, which can be either continuous or discrete. And finally, this gauge group can be realized either linearly or non-linearly. And actually, the interesting case I'm going to slowly is this in blue. So local, discrete, and non-linearly realized. And this will be modular invariance. But before jumping there, okay, I have my superpotential. I know how the fields transform. So the U-covers, they should balance the transformation of the fields, and indeed, no, you see that they should be nothing but homogeneous weighted polynomials of these z variables of a certain power, which is given by the sum of weights or charges of right-handed, left-handed quark and the Higgses. Now, let's discuss a bit differences between linearly versus non-linearly realized symmetry. So if this symmetry gamma is linearly realized, then these transformations, they are just functions of the group elements. And then I have simply that the matter fields transform, let's say, with certain charges, and these scalars, they transform with different charges. I can write also my Keller potential. This is pretty standard form. And then the invariance of the standard potential requires that this vector supermultiplet, the standard model component, stays invariant. And if we have some BSM component, it should transform in this way depending on the transformations. Now, if I have instead non-linearly realized symmetry, my transformations and the scalars, they actually depend on a new player, on a new field, which I will call tau, and this tau undergoes a nonlinear transformation under this, let's say, gauge group. So now you see the story repeats itself, but when we encounter lambda and z, both of them, they depend on tau. And also in the Keller potential, we will have another piece which depends only on tau and tau dagger. And this should stay invariant up to so-called Keller transformation, because when we integrate over whole superspace, holomorphic function of fields just vanishes upon integration. So let me give you a particular example. So linearly realized U1. So then this lambda is nothing but a phase rotation. Zeta elementary scalars. So I have these transformations we already see. So then the waves of these scalars should break spontaneously U1 and CP. And that challenge is to build U1 and CP invariant, let's say superpotential, which realize the desired vacuum alignment. However, if I have non-linearly realized modular symmetry, so here I have many questions. So what is this symmetry? What is this tau I introduced? And how this lambda and z look like? So I will address these questions in the second part of my talk. However, let me anticipate. So a modular invariance is appealing, because in this setup, both modular invariance and CP will be broken by the wave of a single complex scalar, this field tau. And somehow I said that we need multiple scalars to have physical CP violation. And indeed, these multiple scalars, which are now composite, they will follow from the mathematics of this modular invariance. But now let's go step by step. So modular invariance actually is not so usual to encounter in field theory in the bottom-up constructions. However, it appears very often from top down when people compactify string theory models. So in particular, superstrings, they require 10 dimensions, of which 6 have to be compactified. So one of the simplest compactifications is on a product of 3 two-dimensional tori, and actually each two-dimensional torus is mathematically isomorphic to a lattice in a complex plane. And this lattice actually is parameterized by 2 basis vectors, omega-1 and omega-2. And now if I take the ratio of these complex numbers, I also get a complex number which is called modulus. So basically, to be a bit more explicit, so if you identify this side with this side and this side with that side, you glue them, you indeed obtain torus. And this lattice, and hence torus, is left invariant by so-called modular transformations. So these modular transformations, they are non-linear transformations, linear fraction transformations, which take tau to a tau plus b over c tau plus d, with a, b, c, d being integer numbers, and the determinant of this matrix being 1. So indeed, this tau is this something which will promote to let's say superfield or to a scalar field, and it undergoes a nonlinear transformation. So now these transformations, they form an infinite discrete group, which is called modular group, and viewed as a group of matrices, which is nothing but SL2Z. So 2 by 2 matrices with integer elements and unit determinant. So this is huge infinite discrete group, but it can be generated in terms of only 2 elements, S and T. So this S, when acts on tau, realizes so-called duality transformation, so is inversion up to a sign, and T is a discrete shift symmetry, so it shifts tau by 1 unit. Now, tau in principle lives in this complex plane, in upper half complex plane. However, by virtue of these modular transformations, all values outside of this shaded region can be mapped inside by modular transformations. And no values inside of this region are related by a modular transformation. So this shaded strip here is called fundamental domain. And in principle, if you think about this tau as the VF of a scalar field, for any value of tau, modular symmetry is broken, and usually it's broken completely, except for these 3 points, which are highlighted here in blue, where some residual abelian symmetries are preserved. Okay, so now this modular group is nice because it has nice associated functions to each, so-called modular forms. So modular forms, they are holomorphic functions on this upper half complex plane, which transforms under the action of modular group in a certain well-defined way. Basically, if I send tau to gamma tau, this modular function, z, or modular form, goes to itself up to so-called automorphic function, which depends on the modular transformation on tau. And this kappa here, this k, is the so-called modular weight, which should be a non-negative even integer. So to my fortune, or to our fortune, these functions, they have been studied since long ago by mathematicians, and in particular, all of them can be written in terms of so-called Eisenstein series. So Eisenstein series is some infinite sum over lattice, is a special function which has these nice transformation properties. And any modular form of any given weight can be written as a polynomial in terms of only 2 basis functions, E4 and E6, Eisenstein of weight 4 and weight 6. So to be more concrete, I said weight should be even non-negative integer. So if weight is 0, there is only one modular form, and it is constant, trivial one. Weight 2 is special, so there is no modular form exists. 4 and 6, our friends E4 and E6. Then up to weight 12, we have only one basis function, always expressed in this E4 and E6. Weight 12 is special because there are 2 linearly independent modular forms, namely E4 cube and E6 square, and this will be important. Okay, now let's go back to physics. Here I have my n equals 1 SUSY action, and then I already said that tau transforms in this nonlinear way. So now it's promoted to a dimensionless superfield. And matter supermultiplets, they transform very similarly to modular forms. However, now these weights can be also negative. And if you remember from some time ago, then this lambda, this transformation, which is non-linearly realized, actually, you see, it depends on both, on gamma, on C and D, but also on tau. And vector supermultiplets, they also have well-defined transformation. So now if I require the invariance under this modular symmetry, then the superpotential and gauge kinetic function should stay invariant, and Keller is allowed to modify by this Keller transformation, which is a holomorphic function of tau and matter fields. So now let me give you some concrete examples. So it's easier to write actually minimal Keller potential. This is not most general Keller potential compatible with modular symmetry, but it is sufficient for our purposes. So you see there is a piece which involves only the modulus tau, and then the kinetic terms for matter fields M but also you see that tau is involved. So for each tau, actually, these kinetic terms, they are not canonically normalized. So I will come back to it later. Now the main player in the game is the superpotential. So I know how the fields transform, and I conclude that my Yukawas, which are now tau-dependent quantities, so they field-dependent quantities, they should transform as nothing but modular forms with a well-defined weights, which are written here. And this realizes in particular this general discussion I had before. So now each element of Yukawa matrix is a modular form up to some real constant, real because I also imposed CP on my theory. Finally, gauge kinetic function is also real, again because of CP, and the bare theta QCD vanishes. Okay, 2 words about modular invariance and CP. Actually, we studied some time ago in the context of flavor model building. But basically, just to summarize, fields under CP, they get conjugated as should be, well, tau up to a sign because of our convention, and modular forms, which you can think about them as these composite scalars, which depend on tau, they also get conjugated. So now the question, where CP is conserved in this fundamental reach? Actually, it should be conserved up to a modular transformation. And then if you think for some time, you end up with this result. So CP violated everywhere except for these green lines, which are boundary of the fundamental region and the imaginary axis. So as long as I'm outside of these lines, I break both modular invariance and CP spontaneously by the worth of a single field tau. So this is nice. Okay, now let's go back to the Quark mass matrices. I said that each element of the Yukawa is a modular form, and the determinant, since it's a product of the elements, and we know that the product of modular forms is also a modular form, also the determinant will be a modular form of a specific weight, which one can compute, and it is not in the weight I already had before. So it's a sum over right-handed and left-handed quarks over all generations and over, okay, 3 times heaps. So now the relevant quantity is the product of up and down quark mass matrices, and it has this weight given by this sum. And so now, if this weight is 0, I said the only non-trivial modular form of 0 weight is a constant, which is real because of CP. So now, okay, the problem is solved. But one can maybe wonder, so somehow I get what I imposed. And it is true, but now I want to show you that there is actually a very nice consistency at the quantum level for this equation for 0 weight of the determinant to hold. And as I mentioned, the kinetic terms, they are not canonically normalized. So for each VF of tau, one needs to normalize kinetic terms canonically. And if we look at how modular invariance acts on the fermionic components, which are inside of these superfields, you can see that actually modular transformation realized on these canonically normalized fermions is nothing but phase rotation, which depends on tau, and tau in turn depends on x. However, phase rotations on chiral fermions, they are usually dangerous because they lead to anomalies. And this is not an exception here. So we have also mixed modular standard model anomalies. And for theory to be consistent, these anomalies must be cancelled. And here I write the conditions on this modular weight. You can think about them as charges to cancel mixed modular QCD anomaly, modular SU2 anomaly, SU2 weak, and modular U1 hypercharge anomaly. And you see here in particular, we have this sum over quark weights and left-handed, right-handed quarks over all generations. So simplest solution to this anomaly cancellation condition is just to cancel the anomaly across the generations of all fermions, I assign the weights minus k, 0, k across the generations, and assume that the sum of the Higgs weights is 0. So then if you look at them, you notice that actually the condition for cancellation of modular QCD anomaly, this A here, plus this requirement for Higgs weights to sum up to 0, implies nothing but 0 weight of the determinant of the full Quark mass matrix. So somehow the message here that the consistency of the theory at quantum level ensures the fact that the strong CP problem is solved, namely that the determinant of Quark mass matrix has 0 weight. Okay, let me exemplify it by a simplest example, which realizes this proposed mechanism. So I assume Higgses to be not charged under my modular symmetry and assign to quarks left-handed and right-handed the weights minus 6, 0, 6. Then it's easier to write the Yukawa matrices. So in particular here, no, I say that the weight should be balanced. So 6 plus 6 is 12, should be balanced by minus 12. But there are no modular forms of negative weight, so I put 0. So these zeros, they are protected by symmetry. Then on anti-diagonal, I have real constants, real because of CP, and complexity sits in this lower triangle block where I have E6 in the 2, 3, and 3, 2 elements. And this is why I mentioned it was important. Here I have modular form of weight 12. So I have a linear combination of E4 cube and E6 square. And it's important because their phases are different. And this is really what provides physical CP violation. Okay, then I need to canonically normalize my field. So then I pick up these factors of 2 imaginary part of tau, which also help to get hierarchies in quark masses. And the determinant is clearly real and can be made positive. So then, okay, I fix tau. I treat it as a free parameter. In principle, there should be some dynamics which fix the value of tau for me. But till now, I treat it as a free parameter. I fix it to some, let's say, random value, not so distant from tau equals I, and fix also tangent beta to 10, perform a numerical analysis of these mass matrices, and nicely find that I can accommodate all quark masses, including their hierarchies, all mixing angles and delta CKM with coefficients, free coefficients of comparable size. So somehow it's similar to Frogat-Nielsen. So at this point, I cannot say I solve the flavor puzzle, but it's nice byproduct, no? Because I solve the strong CP problem, and also I'm able to explain quark masses and mixins with other, let's say, the coefficients of comparable order. Okay, this setup can be extended also to leptons. So, okay, I assign the same simple charges to them, weights, and assume Weinberg operator for neutrino masses. The textures are all the same. Again, I perform the numerical analysis and find that I can accommodate charged lepton and neutrino masses and mixing angles, including also CP violation phase in the PMNS matrix. Okay, so this works. The number of parameters, many, but they are of comparable order. Okay, then one can go and increase in absolute values this modular weight, build alternative models, but the texture is always the same. These 3 zeros in the left upper part, real constants on the anti-diagonal, and then the complexity which sits in this lower triangle. Okay, so now I just want to make some comments about finite modular groups, because till now I worked with a full modular group, SL2Z, which is infinite but discrete group. So now this infinite discrete groups has a certain nice subgroups, so-called principal subgroups. So basically they are like full SL2Z, but with identification that so all matrices let's say, equal 1 mod n, where this n is called level. And then if one takes a full modular group SL to Z and quotient with respect to this normal subgroup, the result is finite. And why it is nice? Because at small level, 2, 3, 4, 5, these finite modular groups, they are isomorphic to permutation groups like S3, A4, it's double cover, S4, it's double cover, A5, it's double cover. And people used, I don't know, since more than 20 years, they used these finite permutation groups for neutrino flavor model build. And so somehow these groups, they also can have modular origin. Anyway, so some years ago, Ferulio revived this field, and now in the transformations, on top of this automorphy factor, I can also actually have non-trivial representation of the finite modular group. And this representation can be finite, let's say doublet, triplet, and so on, depending on the group. So now the invariance of the superpotential on top of this balance of the weights also requires that the product of the representation contains an invariant singlet. And actually recently there was a very nice paper from Joao Pinedo and Sergei Petkov, where they actually asked the question whether this mechanism I described can work if one assumes invariance under the finite modular groups, because the hope was to find the models in which you can have less number of parameters. However, the result is the following, that for the mechanism to work and also to be able to successfully describe quark masses and mixing, the representations must be one-dimensional. So unfortunately, if we want this mechanism to work only with standard model quarks, this representation should be one-dimensional. This implies that still in the Yukawas, one has many free parameters. Okay, they find model which are slightly minimal. So instead of 7 real constants, it has 6 real constants, but still. So then they actually performed a very extensive study. Here just found some viable models, but the minimal number of parameters is 6 per sector plus tau. And also some observations. So modular weights here are rather large, no? 10, 12, and larger. And okay, and somehow the string friends say that it's hard to realize large modular weights. So in string theory compactifications, usually they get smaller weights, like 1, 2, 3, and so on. So then this somehow motivates the introduction of heavy colored states, heavy quarks, because unlike in the Nelson bar and my construction, heavy quarks are not needed. But if they exist, the mechanism also can work. So assume I have chiral, light chiral quarks, and I assign these charges here, and then I introduce a pair of vector-like quarks with these charges. So now the full theory is anomaly-free, and the mechanism works in the full theory as I described before. So the determinant is real, the gauge kinetic function is real, and the theta bar is zero. However, when I go to the EFT of light quarks, here, no, I write the mass matrix for light quarks, which is nothing but seesaw, and for heavy quarks is roughly, let's say, this MHH entry. And here you see that indeed it can happen that in EFT we encounter singularities, precisely as I commented before, if would-be heavy state become massless. So now in my EFT, the determinant of light quark mass matrix does not have a zero weight. However, in the full theory, we have this. But we should be able to see also how this solution works in the EFT. So what happens now? That actually this phase of the determinant of light quark mass matrix is balanced by the gauge kinetic function, which acquires an imaginary part. So here I cannot go to the details, but the bottom line that now in the infrared, in the EFT, the gauge kinetic function is not real anymore, but it is basically acquires this piece which is fixed by the contribution from heavy fields. And then also in the EFT, the theta bar infrared is 0. So in this recent work with Ferruccio, Alessandro, and Matteo, we looked in detail actually in the models with new heavy vector-like quarks, and we extended the original Nelson bar proposal. So let me briefly discuss it. So let's focus on down quark sector. I introduce SU2 singlet vector-like quarks, this D prime and D prime C. Then in my superpotential, on top of this standard model contribution, I have mixing between light and heavy fields, and then also heavy and light, and also, let's say, Majorana-like mass term for heavy vector-like quark. So the full quark mass matrix is given by this, let's say, block matrix, where the blue blocks, they actually proportional to the Higgses, so they actually, they feel electroweak symmetry breaking, and the red blocks, they are not constrained by electroweak symmetry breaking. So then one goes through the mathematics, and the final answer that the light quark mass matrix has this form. So this seesaw-like contribution, just from integrating out heavy states, and the corrections from wave function renormalization, or saying differently from, let's say, non-canonical kinetic terms. And then, okay, this is a very general setup. Nelson bar limit is obtained in the following way. So the gauge symmetry, standard model gauge symmetry, is broken only in the light sector, and the CP is broken in the mixing between heavy and light fields. And in addition, we have 0 here. So in particular, you can see here that in these Nelson bar realizations, the non-zero delta CKM can originate only from these wave function renormalization factors. Okay, so I'm approaching the end, but before concluding, let me present you with some concrete model we did. So we add new vector-like quarks of D and U type, and now, so we can have actually very small weights, so 2 in the absolute value. So -2 for standard model fields and +2 for this new heavy vector-like field. In addition, we also can have, let's say, non-singlet representation under this modular S3 symmetry. Then, okay, one goes through the math. You can see, actually, I will not go to the details, but you can see that all these blocks, they have this 2+1 structure because they fill this two-dimensional representation of S3. So, and then in the full theory, it's easier to see that the determinant is real and can be made positive. In the EFT, it's a bit more tricky, but again, the mechanism is that the contribution of light quarks is cancelled by the new gauge kinetic function. So also in the EFT, theta bar is 0. Then, okay, we also performed the numerical study. The nice thing that the model works, and we can indeed have lower weights, so maybe those which can be realized in string theory compactifications, and also we can have non-abelian structure, let's say with this doublet here. However, admittedly, we still have too many parameters. Namely, we have 15 dimensionless parameters in both up and down sector plus the modulus to fit or to describe 8 dimensionless observables, basically quark mass ratios, mixing angles, and CP violating phase. So there is still room for improvement, but this is just a proof of concept that also, let's say, a finite modular group and low weights can work. Okay, final word about corrections, because of course I tried to convince you that with this modular invariance and CP symmetry implemented in a supersymmetric QFT, I can have theta bar 0 and non-negligible delta CKM phase. So here I show the hierarchy of scales. So we have Planck mass, then the scale of flavor and CP symmetry breaking, then somewhere scale of supersymmetry breaking mediation, then the superpartners, of course, they should not be at TV, maybe they are 10 TV or 100 TV or so. And then finally the weak scale. So now, as long as supersymmetry is unbroken and modular invariance is unbroken, everything is good because the modular invariance is very powerful. It fixes completely the functional dependence of the superpotential on time. So this is not true for the Keller, but very nicely, actually this theta bar parameter is insensitive to Keller, so it's holomorphic observable. Unlike the masses and mixing angles. Finally, there are also no normalization theorems thanks to Susi, which say that if theta bar is 0, then as long as Susi is exact, it does not run. So very good. However, of course, Susi has to be broken, probably not at low scale, but some higher scale. And Susi breaking corrections in general, they are dangerous. However, there is specific regime which relies on separation of scales between the scale of modular and CP symmetry breaking and the scale of supersymmetry breaking mediation, like you can think about, for example, gauge mediation. Then if there is this separation of scales, and if in addition soft supersymmetry breaking terms respect the flavor structure of the standard model, then the contribution to theta bar can be estimated. And as you can see here, it is highly suppressed, even if tangent beta is not small. Finally, there are also corrections due to standard model dynamics, but those have been computed a long time ago, and the leading contribution actually is at 4 loops, and it is of order 10 to the minus 18, so here we are safe. Okay, so let me conclude. So I presented you with general conditions to solve the strong CP problem in theories based on spontaneous CP violation. So these conditions, they can be implemented in a bottom-up fashion in a QFT with an anomaly-free local flavor scene. So then I focused on modular invariance as an example of such an anomaly-free flavor symmetry, and this modular invariance is inherent to toroidal compactifications in string theory, so it has this top-down motivation. Then I showed that it can be implemented consistently in a supersymmetric QFT, and the VF of the modulus tau is the only source of both modular and CP symmetry break. So then theta QCD problem gets resolved in 2 steps. Since I require CP, the bare theta QCD is 0, and the argdet of Quark mass matrix is 0, thanks to anomaly-free modular symmetry. Heavy vector-like quarks, they are not needed for the mechanism to work, but if they are present, they can help, for example, to lower modular weights. Finally, corrections, they in principle can be dangerous, but it is not something specific to our models. It's specific to all proposals based on spontaneous CP violation and supersymmetry. And fortunately, there are regimes under which these corrections are under control. Okay, thank you very much for your attention.
Many thanks, Arsenii, for the very nice and very complete talk. Question from the audience?
Yeah, thanks for listening.
Arsenii, can you please explain a bit more regarding the condition that the Susi breaking scenario should comply in order to have theta bar very small or very small correlation below the experimental limit for the...
Right. So basically, this is present here. So first of all, there should be separation of scale between the scale of flavor symmetry breaking, in my case modular. Maybe we can think about something sub-Planckian, 10 to the 17 or 10 to the 18 GV. And then the scale of supersymmetry breaking mediation. No, so if this separation of scale is present, then this is good. And in addition, also we have soft supersymmetry breaking terms. And those, let's say, like in minimal flavor violation, they should follow the standard model flavor structure. And under these conditions, it can be shown that corrections are under control. So if these conditions are not satisfied, in general, one can be in trouble.
In the model that you show with this heavy vector-like quarks, in the feed, the masses, you get these masses, I suppose, around the TV scale, and you cover couplings a bit smaller, or do you make the feed with effective parameters?
Right. So actually, we keep track only of the parameters which contribute to large quark masses, mixing angles, and CP phase. And actually, from this information only, the mass of the heavy quarks is not fixed. So in principle, one can take them arbitrarily heavy and decouple. No, because basically in this feed, we neglect everything which goes as standard model Higgs wave over heavy mass. So this is neglected. And the mass of heavy quarks is not predicted. It can be, actually, I would say it's safe to take them somewhere at the gut scale, because here I also take into account the running, but I use the running of the standard MSSM. So I don't want new, let's say, vector-like stuff or new matter to appear in the running.
So
yeah,
you use the mass of yes? You use in the feed the masses of the quarks at the gut scale because you are thinking UV complete theory, maybe SO5 embedding or SO10 embedding.
Yeah, actually, even here, I don't think about some gut symmetries, no? So I have only a standard model symmetry plus very, very heavy vector-like quarks.
And the reason why you choose the masses when you feed the masses, you consider the input the experimental values at the gut scale is because the mass scale you assume this heavy vector-like quarks to be around the gut scale.
Yeah, basically the reason is that it is unlike neutrino parameters, which to good approximation don't run or run moderately. Quark parameters, they run. So and in principle, this modular symmetry, we don't know the scale at which it is broken, but assume that it is broken at gut scale. So then if it is broken at gut scale, somehow you want to describe the values of quark masses and mixing angles I would have at the gut scale.
I see, because when you, after the Lagrangian that you get, after breaking these modular symmetries,
Yes.
it will be an effective Lagrangian below the scale of breaking of the modular symmetry, so below the gut scale. And then the fields that you use, this HU and HD in the SUSY, in the extended MSC model, will be sub-TV scale. I was wondering why in the feed the experimental value for the quark masses at the MC scale are not used instead of the gut scale, because usually the experimental masses of the quarks are at the gut scale. Usually is when one has this gut model or Partisalan models.
Well, yeah, because we somehow have in mind that this flavor symmetry is broken at high energy, let's say at the gut scale, and
the gut scale.
Yeah, the patterns of mass matrices we get, they are somehow at the gut scale. So then it's better to describe what we would expect at the gut scale, because then we know that by the standard, let's say, MSSM running, at low scale, we will have the experimentally observed value.
I see. And regarding in this model, have you considered the extension to the neutrino sector? You consider Taiwan CISO or another mechanism?
So in this particular, we did not, because here we focused only on quark sector, but yeah, the simple neutrino extension is this one, basically just to introduce the Weinberg operator, no? So here we did not elaborate how it is generated, and then you get the same textures, but interestingly, you also can describe the neutrino data. Actually, you can see here that the coefficients, they are not so comparable. So they are something a bit more hierarchical, and this is related to the fact that the neutrino mixing angles, they are very different from the quark mixing angles. So if somehow I can, if I manage to describe quarks with order 1 parameters, then I would expect that in neutrinos I should have something slightly different.
Do you get some correlations in the quantum lepton sector? Because maybe despite there are usually in some model when there are more parameters than observable, but the number of parameters is not too much large, maybe in some cases there can be correlation.
This is a very good question, and actually one would need to investigate, because, for example, here I have a lot of free parameters, but it's true that I fix tau to the same value, so somehow I'm in the same sitting in the same point in the moduli space. So in principle, probably that in the models, let's say with non-abelian symmetries, it's still the hope to find something with which works with less number of parameters, then one would expect certain correlations between this mass mix and observables. Moreover, maybe between, let's say, observables in quark sector and in the lepton sector. But I don't have an example.
Maybe also the correlation in this effective parameter for neutrino beta decay in this model. Maybe it could be used to.
In this particular we did not study it. In the previous our works also with Joao, who is in the audience, and other colleagues, there we worked indeed with these finite modular groups focusing on the neutrino sector, and there we indeed studied also correlations only in the neutrinos and the implications for neutrinos double beta decay.
Very nice. Many thanks, Arsenii.
It's a bit mathematical, but I hope I did not. I tried. Okay, I tried my best, but this subject is a bit mathematical. I find it interesting also. So
very interesting. Yes, I like this topic.
Questions or later, just drop me a line, and I will be happy to think about them.
Question from the audience? More questions? Question from the audience? Another question. There is a particular reason why you choose tangent beta equal to 10 and not 100, or is the most just a benchmark point?
No, it's basically there is no particular reason. We can choose at 5 or 10 or something else, but why we choose, for example, I choose 10 because I know those people who basically, let's say, Antush and Maurer and also Ross and Cerna, which compute the running, they give the values, let's say, of quark masses and mixing angles at some at some scale, for example, assuming tangent beta 10 and certain. It's just to use these values, basically.
Joao, please.
That is Joao. Thank you.
Oh, yes. Very nice talk, Arsenii, sir. I couldn't start from the start, but I actually have a question about this. So, because we see that the quarks, massive and mixings could run a lot, no? But what is your intuition about the chart of the leptons? Because you say, well, maybe don't run so much, but could we maybe play with time beta, traction corrections, and make things run?
What I can say that the only thing that if we, for example, we use this, and this assumes MSSM running. So then if I introduce, for example, new heavy vector-like quarks, I'm better to put them at the gut scale or higher, because otherwise I need to recompute running. And I did not do that, no?
Sure. Now I was thinking about the lepton sector. How much it could change.
Yeah, I don't know, because you mean in the leptons?
It didn't run so much.
In the leptons, somehow we, and also I think not only we, always use parameters at, let's say, at low energy. There are certain scenarios, let's say, if the mass ordering of neutrinos is inverted and largest neutrino mass is greater than 0.1 or whatever, EV or 0.01, EV and tangent beta is large, then the running can be sizable. So then, yeah, maybe is also in favor of not taking tangent beta too big if one does not want to go through all this machinery of recomputing the running. But yeah, purely from this setup, unfortunately, so tangent beta for me is another free parameter.
Thank you.
Joe,
Okay.
you're muted. You wanted to ask another question?
No, I just wanted to thank Arsenii for his nice reply.
Thank
Yes.
you very much for joining.
More questions from the audience? If there are no more questions, we send Arsenii for the very nice and very complete talk. Thank you very much, Arsenii. Very
Thanks
nice
a
seminar.
lot for the invitation and for listening.
Thanks a lot.
Let's go to see the second half of England, the Netherlands.
The football match. Yes, enjoy.
Okay, thank you.
Are you going to ICHEP conference?
Sorry?
Are you going to ICHEP conference?
No, unfortunately not. I already went to several conferences this year. So just recently, last week, I went to the Invisibles workshop. And then I went to some other workshops. So now I will pause.
I see.
No
So
other
I will be
conferences
another conference.
in the near future. Are you going there?
I am going to ICHEP, yes.
Where is it?
In Prague, next week.
In Praga. Very nice. Maybe
Yes.
Joao.
I'm not going, unfortunately. Also, I spent all my mission money. I'm going to now in September.
You're going now. Today?
Sorry?
What you mentioned, Joao?
I'm saying I'll go to now neutrino oscillation workshop in September. But otherwise, I exhausted my budget for conferences. So I'm also not going to ICHEP. There are some people from my group here in London that will go. Maybe Matteo Pavicciato, also Arsenii's collaborator, will go.
Pavicciato, yes.
Yes.
Maybe
One of the authors of this.
Yeah.
Okay.
Thank you very much, Arsenii.
Yes, thanks a lot, and thanks a lot for joining. And hope
Thank you.
to see you soon.
Bye, guys.
Ciao.
Bye. Have a nice time.
Ciao.
Bye.
Buona serata. Buon pomeriggio.
Buona serata. Buona serata.